So we'll start the session at 6:10. Let if other joins, we'll start at 6:10 only. Okay. Okay, so let's start the session. So today we will be discussing about the week 8 lectures of the course Watershed Hydrology, and we'll be doing some assignment questions so that it more becomes more clear and helps you to do the assignment questions for this week. So till now, what all we have discussed? We have discussed the basic of hydrology, like what is hydrology, what are the hydrological components. Then we have studied in details about those hydrological components, how we can measure that, what are the applications, and so on. We have studied hydrograph. We have studied the hydrological components like precipitation, evapotranspiration, and runoff, stream flow, and so on, right? And then we have moved to watershed and watershed. What are the watershed characteristics and so on. So now we know the basics of hydrology. We know the physics or the processes that is behind those processes, that is hydrological components in the water cycle and so on. So with that, we'll use those physics or the process that we have learned in something called models or hydrological models. So we'll start this. I hope you guys have gone through the week 8 lectures. So in this week, we have studied about the hydrological modeling. What is hydrological modeling? Why it is necessary? Where we can apply the concept of hydrological models, and then with those we have also seen machine learning models and so on, right? So okay, so with that, let's start the session. Hello everyone, I am Balram Shah. I am the PMRF TA for this course, that is Watershed Hydrology, given by Department of Food and Agricultural Engineering from IIT Kharagpur by Professor Rajendra Singh. So I'm doing my PhD at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So I'll just stop sharing from here and I'll switch out the video so that take proper video. Okay, yeah. So if you guys have any questions or any queries related to previous assignments, also you can ask. Okay. So start sharing from here. Give me a minute. Yes, I can see the screen. So before moving on to the question, let's see some problems first. I mean, what we have studied as a summary kind of, right? So we started with the something called model. Oh, sorry. Yeah. So something called model. So this word model, or you can understand was from the word literal meaning. What you can say, what is a model? A model is a simplified representation of something real but with some essential features. Correct? So models can be, a prototype can also be a model. So let's say a big dam and you want to study like how the sediment is behaving in this dam. So let's say if you are making a prototype, you can't make a big dam kind of structure in your laboratory, right, to do the experiment. So for that, what you can do, you can either go for some prototype kind of model. So you can create a miniature of that dam, and then you can see how it behaves if you scale everything down to some scale, to the miniature scale or to the prototype scale, and then you can understand how it will behave. So let's say if we are opening the sluice gate, how it will affect the downstream, or let's say the sediment load, how it will affect the downstream section, and so on. So like that, for several other applications, what we can do, we can't we can't go for every, like, if it is a big area. For instance, let us consider a watershed, a big watershed, let's say Ganga watershed, right? So in Ganga basin, you can't go at every point of the Ganga basin to understand the feature or the hydrological components or some behavior of that watershed. So for that, what we can do, we can create, or we can develop some models with which we can get to the information that we need for applying that to some problems that we are facing in the basin and so on, right? So this models in context of or hydrological model. So a model which is made specifically to understand the hydrology or the cycle or the hydrological components, we call that model as hydrological model, right? Now again, this there is two terms. First term is modeling system, and the second term is model itself. Okay, so modeling system and model, there is a very minute difference between this. So what is this modeling system? Modeling system can be some software. In any software, for example, SWAT or WIC model or HMS, HECRAS, there are a lot number of hydrological models that are available in the market, right? So these are what? These are the softwares, and software will have what? Software will have the array of equations that simulate watershed power processes. So let's say you in the hydrology will have water budget equation, then energy budget equation, then several equations that we have studied uh, throughout the course. So if we uh, impose all the equations and make one software in which all these watershed processes are simulated, we call that software as modeling system. Okay, so that is modeling system. And now what is model? Model means that software, if we give the input data to it, so that we can uh, use that equations to get the output. So this software or the modeling system with the input data specific to the watersheds, for let's say climatological data such as precipitation, temperature, relative humidity, wind speed, and so on. Then topographical, like slope, dam, and all. Hydrography, soils, land use, all this data, if you put in the modeling system, we call that as model, right? So now this hydrological model uh, can have this mathematical modeling process. So as I just mentioned, that the modeling system or the model will have the equations in it, right? So it will be a mathematical model. Now for this mathematical modeling process, there will be three terms. First is the formulation, second is the deduction, and third is the interpretation. Okay, so let's say a real watershed, for instance, let's say Ganga basin. So to create the model, what we have to do, we have to do the formulation, or we will have to formulate all the equations that we have. Okay, so we'll do the formulation of the real system and we'll create the model. Okay, right? And then from the model we'll deduce some conclusions, so that process is called deduction. And from the model conclusion, we'll interpret that and we'll understand that how this real world behaves, or the real watershed, let's say, for instance, behaves. Okay, so that process is called the interpretation. Okay, so what is formulation? Formulation process is involves translating the understanding of the hydrological system of, let's say, the real world scenario into the mathematical equations. That is the formulation. Then what is deduction? Deduction phase means it includes several steps that integrate scientific principles, empirical data, and mathematical equations to represent the behavior of the hydrological system. Okay, so this deduction, there will be several iterations, so that we can lead to the uh, very near to the solution. So there is a saying like no model is perfect, and no model is perfect, right? Because what we are doing, we are representing the real system or real world scenario to some extent, right? So we can't fully represent the watershed because uh, the natural systems, till the time we can't say with 100% probability that we have understood all the processes of the real world scenario, right? So we can't represent the whole thing into the model, so we have to keep some assumptions, we have to have some limitations of the model. So with that, any model which we are using is specific to the application which we want, right? Okay, now come to the interpretation. What is interpretation? Interpretation involves analyzing the results that we have drawn from the deductions, model deductions, and drawing meaningful conclusions about the behavior of the hydrological system. So with this, we have the mathematical modeling process. Okay, so what we are doing, we are taking the real world scenario, for example, the watershed, real watershed such as Ganga Basin. Now, in that, what we'll do the formulations with all the physics that we have learned, such as the water budget equation, energy budget equation, and so on. And with that, we'll make the model. So that process is formulation. Now, what we'll do, we'll have that model, or we'll run the model, or we'll simulate the model such that we get the conclusions or the inferences from the model. So that process we'll call that as reduction. And now we have all the conclusions. From there, we'll again understand that how the real world or the real basin behaves. That is the interpretation. Okay. So the principles of modeling are what? As I said, no model is considered to be perfect, and hence a model should never be taken like very literally. So whatever, for whatever purpose that model has been made, we need to understand that. So from the beginning of this tutorials, I have reiterated as it so many times that whenever we are using some process, some methods, we should know that what are the assumptions behind it, so that we can know that where to use those methods and where not to. Similar to that, we have to understand that what assumptions are made into the model, and hence we should use those models in the respective domain or in the respective applications. Okay, so a model should neither uh, pressed to do or not criticized for failing to do that for which it was never intended, right? And also this model cannot replace decision makers, because they will help in the making the decision, but will it will not it, because you will understand that okay, these processes are involved, and from this we can find these conclusions, and hence we can make these kind of decisions. Okay. Okay, so with that we'll see some modeling protocols. So what are modeling protocols? Modeling protocols are the steps that are involved in the hydrological modeling. So what are the modeling protocols? So firstly you have to define the purpose, like for what you want this model, for what purpose you want. So we call this as perceptual model also, this section. Now, after you have defined the purpose of for what you are going to use the model, what you have to do, you have to come up with the field data, and you have to conceptualize it. So you will get the conceptual model, right? Now you have conceptualized like how the model will behave and so on. So from there you will go for the numerical formulation. We'll do the coding or computer programming, anything what we will do. So we'll do the development of the code. Now after the code has been developed, we'll use that for constructing the model. So we call that as model construction. Okay, or we say model setup. Okay, so now after the model setup has done, we need to check whether the model is, wait, it is not showing here. Okay, yeah. So after the model setup is done, what we have to do, we have to calibrate and validate those models. So okay, so we'll see the we'll do the calibration and validation and testing, let's say. And then if we see that it matches the performance criteria, we'll see all this one by one. Anyway, we have gone through this in the lectures. Performance criteria, if we are satisfied with the performance criteria that we have given, then we'll consider that model and we can do predictions or forecasting of whatever hydrological components we have. Okay, or else what we have to do, we have to again calibrate the model and calibrate, validate, and then again we have to see the performance, and reiteratively we have to do this unless until we are satisfied with the model setup. Okay. Okay, so with this, so what are the so with this, what you can say, what are the advantages of the model? What are the advantages of these models? So, anyone? So from the models, what we can do, we can model a complex system into a computer programming with the help of computer programming or simplified representation of these complex systems, so that we can understand in a better way that how the hydrological system behaves or interacts. Right. This is one of the advantage. Then because we can't go every time to the field and we can take everything for any of the inferences, what we can do, we can do the model in the computers, and hence it will be a cost effective analysis. So it will allow us to explore the scenarios and assessment of outcomes without the need for expensive and time consuming real world experiments. So we can just change or tweak some of the parameters and see how it will behave, or how it will change the results. So let's say uh, there are several climate change scenarios, and for each scenario we can run the model. We can understand that for these climate change scenarios how the catchment will behave and so on. Okay, so understanding complex system, then cost effective analysis. Again, write that. Advantages are understanding the complex systems, then cost effective. We can do the prediction. So let's say for flood or drought, we can do the prediction or forecasting. We can do the risk assessment of any of the structures or something like that, and so on. Right. So but there are several disadvantages also. Can you guys identify one of the disadvantages of hydrological model? So while explaining only, I said that each of the model has some of the assumptions. So let's say I am working on a very large scale model, right? So in that case, some small components which for a larger temporal scale or for a large time scale, let's say for a annual time scale or for decadal time scale, small hydrological components such as maybe infiltration or something like that will not be affecting that much in the watershed. So this is one of the assumptions that I am making. It might be possible that it is not true to the real world, right? So the simplification and assumptions that we are making while creating the uh, model, that is, that can behave as the disadvantage of the model. Okay. Then we need intensive data for the models. We have several calibration challenges because mm, the parameter, we'll see what is calibration, then we can understand this. Then uncertainty in the predictions and so on. Okay. Okay. So till now, is there any question? If not, I will do some questions. Assignment question. Then we'll come to. Okay. So the first question is, dash is a simplified representation of something real but with essential features. You tell me what it is. It is simple only. Just now we have seen that it is a model. So a model is a simplified representation of something real but with essential features. Correct? So correct answer will be B. It is modern. Okay. Next we have. Next question didn't come here. Okay. So the question is dash is a process of mathematical model in hydrology that involves analyzing the results and drawing meaningful conclusions about the behavior of the hydrological systems. So we have seen the process of mathematical models, right? What are those? Formulation, deduction, and interpretation. Correct. So in that, what it is saying that which process involves analyzing the results and drawing meaningful conclusions about the behavior of the hydrological systems. So now we have the results. This means we have deduced or we have done the deduction for the mathematical process. After that, what we have to do? We have to understand that, or we have to infer that what conclusions we can find out from the output that we have got, right? Like how the hydrological system is behaving. So that process is called interpretation. Correct. So the correct answer will be C. That is interpretation. Okay. Any question here? Okay. If not, we'll move to the next question. Next question is an empirical model is called. So we have not done this. We'll go to the questions. Okay, so we have now understood what is a hydrological model and what are the advantages and disadvantages of hydrological models and why should we use hydrological models. The importance of the hydrological models we have understood. Now we have to understand that where, like in what all aspects of hydrology or hydrological sciences, we can use these hydrological models. So now is the applications of hydrological model. Okay, so there are several now you understand what is the importance of hydrological model, right? So with that only you can tell me like where all we can apply in the hydrology. Most like in all the um, like whatever you can think in the hydrology, mostly you can uh, form a model. It might not be a mathematical model, it can be some empirical model, it can be some conceptual model, but you can develop a model for each of the hydrological process that you can think of, or any water resources, any water resources process you can think of, you can model it, okay, with all the process that are involved in it. So we can do for planning, design, and operation of projects. Then soil and water conservation. Then not only that, water quality aspects and so on. Okay. Watershed management that we have studied in the last lectures last week, right? And so on. It can be rainfall runoff model and so on. Correct? So it can be in all, as I said, it can be in the all the aspects of water resources assessment, such as like let's say if you want to create a rainfall runoff model, you can create that rainfall runoff. This runoff is the surface water kind of thing, right? Surface water model. Maybe for agriculture, if you want, you can create some irrigation model. Then soil erosion for soil conservation. Then water pollution, groundwater, and so on, isn't it? So these hydrological model consist of two components. First is the hydrological code in which we understand the process of the hydrological cycle. So whatever scientific basis we have for the process description, we'll do this in hydrological code. And the second component is the technological shell. Okay, so in technological cell means what? So whatever process that we know, that we have to code, or that we have to um, program, so that we can make a software, or let's say some programming in which we can create a model. So for creating a model we need um, to program it, to make a user interface, or let's say to make a pre or post processing facilities and so on. So that is covered in the technological shell. And this, so for technological shell also you can say these two components are interrelated, because if you know the process, then only you can program it very efficiently, right? So these are the components of the mathematical hydrological models. Okay, so why these mathematical models are very much preferred and why we are giving time to it, because it will help in rapid development with scientific basis and application. Because whatever science we have, we need to model it so that we can get real output or real conclusions for the real watershed. Okay, and these models nowadays are universally acceptable. The whole globe is almost working on it. Okay, now coming to the classification of models. Okay, models, or let's say modeling approaches, I'd say. So modeling approaches can be classified on the basis of, it can be based on the process involved, or it can be based on the time scale that you are working on, it can be based on the spatial scale that you are working on, okay, and so on. So let's say first is the processes involved. So we should understand all the classifications properly, because whatever model we are creating, we should understand that how it will behave. So in these processes involved, it uh, can be mathematical solution, as I mentioned in the mathematical models, mathematical solution. So now these mathematical solution or mathematical model can be developed in many ways. It can be like, so let's say if for one watershed you have a data for 30 years. So let's say you have the precipitation data set, you have the runoff data set. Okay, now what you can do is you can just assume one kind of relationship between the uh, runoff and rainfall, and then you can put that data. So let's say if you assume something like q is equals to a r to the power b, something like this, for example. Okay, now what you can do, you have the data for q and r for 30 years, let's say. Okay, now you can, what you can do, you can maybe linearize this, or you can put those data and you can find out the parameters here. A and b are the parameters here, because it will only change. Now let's say if the rainfall is the independent variable and q is the dependent variable. Now if you know the rainfall, and if you change the parameter, then only it will change the uh, let's say runoff, right? So you need to understand, you need to know this a and b. So these are the parameters here, right? So what you can do, just from the data and assuming one relationship, you can find out, or you can create, or you can develop a model. We call that as empirical model. Okay. So in empirical model, what after creating the model, what you can say, that it is one input output relationship, and as we are not involving any physics in this, so there is no physical meaning to it. Okay. Empirical model is clear. Okay. Okay. So the next is, in the mathematical solution, is a conceptual model. So in conceptual model, what we do in conceptual model, some of the process we represent, and like mostly we can conceptualize, right? And third model that we have, which is mostly gives you the physical meaning, are called process based. So in process based, what we have, whatever fundamental physics or the basic physics that we have learned in the hydrology, based on those equations or those fundamental basis or governing processes, right? So based on the fundamental physics or the process that are governing those or the governing equations, you can say, based on that we have process based model. So in process, if you just see process based model and empirical model, what do you think, in which model it will be, the output will be much more uh, performing better than when you compare it with the real observation data? Anyone? Because see, in the process-based model, we are also incorporating the physics in it, the process that are governing those output, right? So in that case, it is expected that in process-based model, the output will be much more realistic, or much more. Uh, it will much more show you how the real world behaves. Correct? Okay. So these are the mathematical solution. Then in process, based on the processes, we can classify it into nature, like deterministic. So the deterministic model is what? So let's say you have created a model as we have seen here. Let's say here in q equals to a at the sorry q equals to a at the power b, right? Now let's say a and b are fixed, a and b are constant. In that case, what will happen? That if you put r as 10, okay, so let's say you know a and b, okay, let's say a is 2 and b is, let's say, 1.2, something like that. And now for a fixed value of rainfall, that is r, you will get a fixed value of q only, right? So that process is called a deterministic model. So in deterministic model, what we do, a single set of input will generate single set of output. It will not change. So how, whatever number of time you you put that value into it, it will have the same output. Okay. And next is the stochastic model, or you say probabilistic model. Probabilistic model. So in this is a probabilistic model. So based on the probability distribution or the probability, what we get, so some inputs, some parameters or process follows some probability distribution. Based on that, we create the probabilistic model or stochastic model. So let's say we are saying that extreme precipitation or extreme rainfall is behaving a gamma distribution, right? So gamma distribution has its own function or has its own equation. Now, based on the parameters that we have in the gamma equation, that is gamma, for that, probabilistically we can say, okay, for this rainfall, this one will be the runoff, for example, right? So every time you give some input, it will have, it might have different output. It will be in small range, but it will be varying every time that you put the input. Okay, so that is called stochastic or probabilistic model. Okay, so this one, all those, these two were based on process and rainfall. Next one was the based on temporal scale or based on time. Okay, so based on time, it can be steady state. From the, what you can understand, that when some parameters or some variables are, so I'll write that, when variables of the process does not change with time, we call that as steady state model, right? Then it can be event based model. So in the very first or second class, we have first or second week we have discussed about this event based model. Remember that when we are creating hydrograph, we are putting one kind of box here and we are saying that this is one rainfall event, and based on that we are saying okay, this is the hydrograph behavior that we have, right? So this is one event with, let's say, this much centimeter of rainfall for this much duration. We call that as event based model, right? This is also for some duration and hence it comes under the classification of time. Then we have continuous model. Okay, so in continuous model, variables as well as the not the process, variables will change and will be depending on the previous state. So let's say if we say flooding, or maybe some kind of flooding, for example, let's say flooding. So the flooding that will happen on Tuesday, let's say, will also be depending on the rainfall that has happened on Monday and on Tuesday. So here variables can change and can also depend on the previous time step or previous states, let's say. In that case, we call that as continuous model. And there can be several time steps. So time steps we can work on can be hourly. For flooding, even we take it as 15 minutes, 30 minutes, 10 minutes interval. Okay, it can be hourly, it can be daily, it can be monthly, it can be yearly, and so on. It can be annual, it can be decadal, and so on. Okay, now based on this, again, now let's say one model we are creating. Okay, now if we want to work on hourly model, hourly time step, then what do you think, whether the complexity will be more in a model with hourly time step, or it will be, the complexity will be more in a model with annual time scale? Obviously that it will be more complex in hourly time step. Why? Because in hourly time step, firstly, that the data set that you will have, for let's say you are working for 30 years, you will have 30 into like 365 into 24, that many data sets you have. But for annual you will have only 30 data sets, right? So in that case, or 30 data values, for instance, right? So for that, as the data set is a large quantity in the hourly time steps, it will become more complex. Now again, working with this much of data sets will make the programming much more complex, and hence the complexity will increase as you go to the diminishing time scale, or the as you lower the time scale, the complexity of the model will keep increasing. Okay, so this one was based on time. Next we have based on space. Space as in spatially how it is varying. Okay, so based on the space or spatial scale, let's say, we can have a multi-basin study. Multi-basin study means we consider so many basins. So let's say for peninsular India, we can consider, let's say, Kaveri, Godavari, Krishna, Pennar, and so on. Right. So we are considering several basins in one region, in a big region, and we call that as multi-basin study. Then we can have basin study, mostly that we are working in this, or we are studying in this uh, course, is the watershed hydrology, right? So it is mostly on basin scale. Okay, for only one basin, if you are studying something, we call that as basin scale study. Okay, next can be sub-region study. So let's say if you want to understand the behavior only in, let's say, one district of some state, so that is kind of sub-region study. Okay, then it can be spatial detail, like how much detail you put in the space. Based on that you can classify the model. Okay, here we have important classification. First is the lumped model. Second we have semi distributed model, or you can say semi lumped model, somewhere it is mentioned, I have seen. And then we have distributed model. Okay, now you see in lumped model, if you consider some watershed, let's say, right? So in this watershed there can be possible that, let's say this is the watershed, there are several different type of land use land cover which will. So let's say we have studied for like how the forest hydrology behaves, how urban hydrology behaves, right? So every different land use cover will have different um, what you can say, different response, right? So if let's say the land use land cover of the watershed is different, in that case what can happen, that the response at each of the spatial scale, so let's say the response here at this region and the response here might be different, right? So if we don't consider that, we consider that for the whole watershed, whatever rainfall we are getting, and we are what we are doing, we are averaging that. Okay, so only one amount of rainfall is happening uniformly over the whole watershed. Then we call that as lumped model. So just for understanding or just for visualization, you can think a big drop of water, only one drop of water is happening over the whole watershed. You can consider that as the that model as the lumped model. Okay, and in distributed model, what you can say, that each of the, let's say, small uh, maybe grids, okay, like this, like how each of the grids responds to the input that we have. Okay, then for that we call that as distributed model. Okay, then based on the spatial scale, it can also be 1D, it can be 2D, and it can be 3D also. This means what? So let's say if you are considering the watershed, again I will draw the watershed. Now see, uh, this river, I'll call that as one. Now this river, if you can see, this river is happening only in one direction. So if you consider the channel system, then that is in one dimension, right? Now if you talk about overland flow, so overland, what is overland flow? Overland flow is like, so all the flow that is happening on the surface, we call that as overland flow, right? So this is in the two dimensions. Okay, now so I mean, if you consider that this as one dimension, x dimension, this as y dimension, and let's say something like this as the third dimension, then in x-axis we have channel system, in xy plane we have the overland flow, and let's say if you talk about groundwater flow, then that will be in the 3D, because it will have infiltration, it will percolate, it will also flow in the whole domain of the watershed. So that is in the three-dimensional space. Okay, so these are the classification based on time scale, based on spatial scale, and based on the processes that are involved, right? Yeah. So as I mentioned that as you go to the lower time scale, let's say from annual to daily or maybe hourly, the complexity of the model will increase, right? Similarly, if you think about the spatial scale, and I ask you that in case of lumped or distributed, what do you think, in which one of the model the complexity will be more? See, in the lumped model you are considering average kind of rainfall for the whole watershed. So whatever is happening at one region is happening in the other region also of the watershed, right? So in that case, the complexity of the model will be less. Whereas in the distributed model, so for each of the grids, for example, you are working, so the complexity of that will be more. So as you go in the smaller spatial scale or in the distributed domain, let's say, the complexity of the hydrology will increase. Right. So again, as you move from the higher time scale or longer time scale to shorter time scale, the reliance on the process understanding also we have to increase. Like we have to understand in depth of the smaller time scale how the hydrology behaves, how the watershed behaves for some amount of input, right? So same happens in if you go from lump to distributed. So in the distributed, we have to have more understanding of the watershed or the region. Okay, so we need to get a more amount of data, or it will be data intensive or distributed and shorter time scale. right? So yeah, so as the complexity will increase, the computational data will computational requirement will also increase. Okay. Okay. So I hope with till this it is clear. Okay. Yeah. So now these catchment models or watershed model, whatever you can say, catchment models, as I said, it can be empirical model based on some assumptions, empirical model. And as it is empirical model and we have created some equation based on the data only, so we don't know what is the process involved, and hence we call this as a black box model. Black box model means what? Like it is a category of model constructed solely from the observed data, as I said, and it is called black box because we don't know what physical processes are underlying in the hydrological system, and just based on the relationship between the input and output variables, we are getting the uh, outputs, right? So in the black box model, what happens? So let's say some input you are putting. So the system you consider as a black box. So something is happening in this which you don't know, and then you directly get the output based on the relationship that you have. Okay. So in this physical process are ignored. Okay. So just put the input. You don't know what is happening in the inside, and you are getting the output. So that's why we call that as black box model. Okay. Now, if you know all the processes in the involved in this model, we call that as white box model. And let's say if you know only some part of the physical process and you have assumed that some of the hydrological components to be negligible or something, we call that as gray box model. Okay. Okay. So we were on the empirical model. So empirical models, there are a lot of empirical models which we use in hydrology. So what we are doing, so as I mentioned that we have data for some area. Based on that, we have the observed data. Based on that, we are just creating some relationship between the input and output, and we are getting the output. Okay. So there are several we can consider. So there are we can do time series analysis. So what is time series again? Time series means some data which are there for the whole for some time duration, that let's say. So let's say for example we know a rainfall of each day of 1 year. So we know the daily precipitation for 1 year. So now it is a time series data for 1 year, or time series data of precipitation for 1 year. So that is called time series data. Now if you analyze those data, we call that as time series analysis. So we can work on unit hydrograph, then we can do some regression, linear regression or non-linear regression, something like that. Then you can use statistical techniques like ARIMA model, something like this. Okay, I'm not going detail into the ARIMA model and all. Okay, other than that, we are also having some data-driven model. It can be artificial neural network. Something like that. Artificial neural network we have studied in this week. So, okay. Artificial neural network, then fuzzy optimization or fuzzy rule based system, then genetic algorithm, and so on. Genetic algorithm is mostly used to optimize the parameters and so on. Okay, so in this, what we are having, we have some input data. Let's say we have some input data, something like this, something like this. So we have the input data. So we are using maybe some of this as a system. We are taking this input data and we are getting the predicted output for this time series. This is time and this is the output. Okay, so let's say something like this. Okay, yeah, and as I mentioned that usually lumped model, that is variables and parameters, if it represents average values of for the entire basin, we call that as lumped model. And this physical significance is not that clear. Okay, so as the physical, you have to calibrate each of the models. So we'll come to that calibration validation again later. Okay, so I hope all this classification, model classification is clear. And as I said, what is white box model? White box model are like, so you know all the process that are involved in this model. So it is fully physics based model. So this white box model, what it will do, it will describe the natural system using equations. So let's say conservation of mass, conservation of momentum, conservation of energy, based on all of this mass conservation equation, or momentum conservation equation, energy conservation equation, and all. You are creating a model, so you know all the physics that are behind that model. So parameters, whatever parameters will be there in that relationships that have direct physical significance. So let's say if you are, let's say the one that I wrote, for example, now you know this A and B, what is the physical significance of this. So you will know the physical significance of all the parameters that are there in the model. So in that model will be called as white box model or physically based model, right? So it will be usually fully distributed. Okay. Yeah. Okay. So with this, we'll do some questions first, and then again we'll. So we did it here. Sorry. Okay. So the next question is, an empirical model is also called as, just now we have seen. You want to tell? It is called as black box model because we don't know what is the physical process that are behind it. So the correct answer will be B. It is black box model. Next question is, what is the primary purpose of hydrological modeling? Okay, so the primary purpose of hydrological modeling is to control flood events, is to simulate movement of glaciers, to predict precipitation patterns, and to understand and manage water-related processes. So all these three options that you can see, these can be uh, purpose of a specific hydrological modeling which is made just for that purpose. So we can use some hydrological models to control not to control but to understand flood event. To simulate the movement of glaciers, we can create some models, right? To predict precipitation patterns, also we can create some model. But the main purpose that is there for any of the hydrological modeling is to understand and manage the water-related processes. Okay, so the correct answer will be D. Any questions still here? So okay. So the next question is, the process of estimating the model parameters is called. Yeah. So I was discussing about the in the beginning only. I said that after the model setup is done. So this means, what is the meaning of model setup? That with some parameters we have created a model. Okay. Now we have to do calibration, calibration and validation. Right. Calibration and validation. Sometimes validation and testing. Mostly the validation and testing will be seen as the same similar thing. Okay. Now first is the calibration. So this happens after the model setup, right? So model setup means we have created some model, we have developed some model in which there are some parameters are there, right? So What is calibration? If you just write, calibration is the process of estimating the model parameters. Okay, so we have created the model with some parameters, but we need to understand that which parameters need to be there in that model, and we have to estimate the value of that parameters, right? So that process we call that as calibration. Now for any prediction, so let's say if you want to know some output as compared with the observed data, so what you will do for a given set of assumed conditions, so let's say for any of the initial condition or boundary condition, for that you need to find a fixed set of model parameters. So these model parameters can be physical parameter and it can be process parameter, right? Now this physical parameter we have studied earlier. Can you tell me any of the physical parameters that you guys have studied? Anyone? Okay, so the physical parameters we have studied in last week itself about the watershed characteristics, right? So we have studied about catchment area, catchment slope, etc. So these are the physical parameters, whereas the process parameter can be the Mannix-Rough coefficient n, which can be found out through the experiments, or let's say from the model also. Okay, and then average depth of water and so on, right? So there are some physical parameters such as the hydraulic conductivity, then porosity, which are measurable in theory, but it is difficult to measure in practice. And hence, what we do, we often calibrate that. Okay, so we often estimate that parameters. So for here, the process of estimating the model parameters is called calibration. Okay, any question here? Okay, if not, we'll move to the next question. Proxy catchment test. Okay, we'll come to this later. Yeah. So yeah. So the next question is model validation is performed to. So now comes the validation part. As I said, in the after calibration, let's say we have estimated the parameters. We need to know whether these parameters is exactly giving the solutions, or the solutions that we that really shows the process, right? So what is validation? To the process of validating, right? So it is a validation is the process to assess the accuracy and reliability of a hydrological model. So let's say you have created the model. Now you have estimated the parameter, but you need to know that whether this hydrological model with this estimated parameter is accurate for prediction, forecasting, or something like that. So it will assess the accuracy and reliability of that hydrological model. Okay. So in the validation, what we do, we run the model using the input parameters that we have estimated, determined during the calibration process. But what we do, the output, let's say if you have a data for 30 years, what we do, we divide this in, or we split this into two parts. This is one of the procedure that you can say. What we do, 70% of this data we calibrate, and the remaining we use to validate. Okay. Now this validation can be done, calibration validation can be done with some performance metrics that also we have seen. So what we do, the model predictions are compared with the observed data. So this here we also have the observed data, right? So we see whether it is performing well or not. So these, for this we have several performance criteria, right? There can be visualizations such as time series plot, or there can be CDA cumulative distribution. Then other than visualization, we can have some statistical measures, like we can have R square value or correlation value. Then we can also have several efficiencies such as Klee-Gupta efficiency, Nash-Sutcliffe efficiency, and so on. Okay, so based on these kind of performance metrics, we decide whether the validation or the whether the model that we have set up is proper or not, right? So what we are doing with validation, we are assessing the accuracy and reliability of the hydrological model that we have set up. Okay, now move on to the question. What was the question? The question is, model validation is performed to ensure that the model works well for a different data set. Okay, next is adjust the model parameters. Third, remove bias from the model. Fourth, optimize the computational efficiency. Okay, so the correct answer will be here. Ensure that the model works well for a different data sets. That's what we are doing here, right? 30% data we have not given while during the calibration. So the model does not know how this data will be, and we are using the same parameters which we have used for calibration, and then we are checking whether or we are testing whether the same input parameter that we have set up or estimated during calibration works well for the observed data that we have or not, whether it is matching with the observed data or not. So that process is called the validation. Okay, I hope this calibration validation is clear, because this is one of the important uh, part where people get stuck, or there is a lack of understanding in the students. Okay, okay, so we'll move to the next question then. Yeah, so what is the primary purpose of model calibration? I think this is the repetition on this. The correct answer will be, yeah, so the correct answer will be to adjust the model parameters for better accuracy. First is to validate model results with observed data. We know this is validation, right? So to test the model under different scenarios, this is the testing period, and to eliminate the answer also. Okay, so this one C also will be the answer. Anyway, but for that is similar, but that mostly we call as testing. To eliminate uncertainties in the hydrological process. This is calibration part. Or testing is the testing part, validation part. Okay. Okay, next question is, in hydrological modeling, parameters with high sensitivity. Okay, now comes the sensitivity analysis part, right? So, okay, before that, let's explain few methods of the validation. Okay, so before this, we have seen what is calibration, what is validation, right? Now for this, there are several procedures. Okay, one of them I just explained, that first one was the split sample test. So mostly what we do, we split the data into two parts for calibration and validation, right? And before that, we keep some warm-up period also. So warm-up period, in some papers you will find it as spin-off period, some as Hodgson's period, something like that, right? So these are several names. So why we use this warm-up period? So that because it is a model in the initial condition and all, it can be possible that first of the few data sets or first of the few outputs that you are getting is not properly you will not get proper value, and hence you keep some warm up period, and after which the model will behave properly, right? So after warm up period, there will be calibration period where you have data for calibration, sorry, and then validation. So let's say you have data from 1980 to, let's say, 2010. What you will do, maybe 1980 to 1981, 2 years you will put warm up period, then 1980 to maybe 2000, 2002, let's say, you are keeping as calibration, and remaining 2003 to 2010 you are keeping for validation, something like that. Okay, so here what you are doing, you are splitting the sample of the data set that you have. Okay, so one period of observation you are using for model calibration, and other you are using for model validation. So this validation you can do in two parts also, or three parts also, anything that you can, based on what you are doing. Okay, next we have differential split sample test. So in this what we do, So in this we divide the data according to the rainfall rate or some other variable, let's say. And what we do, why we do this, to show that the model has some general validity. For example, let's say we divide it into monsoon and non-monsoon period. Okay, and then after non-monsoon periods for rainfall, let's say. Okay, so what we do then, model is then cross validated. So for example, we calibrate for the monsoon period and then we validate it for. So what we do, let's say calibrate for this monsoon period and validate for the non-monsoon period, and if it works well, we consider that model. This can be one example. One example can be high flows and low flows for, let's say, stream flow. So what we do, we calibrate for the high flows and then validate for the low flows, or vice versa. We calibrate for the low flows and we validate it for high flow, something like that. Okay, so that is called as differential split sampling test. Okay, third is the proxy catchment test. Proxy catchment test. So in this what we do. So let's say you have one watershed. Okay. Okay. So now let's say you have one catchment. So let's say this is a natural catchment. Okay. Now the properties that is there for this catchment. So let's say I'll give the name for this catchment. Let's say this is a catchment A, and we have another catchment which we are working on. Something like this. We'll name this catchment as B. Okay. Now you are working on this catchment, or you are studying this catchment. Okay, now you know that these two catchments, whatever we have, catchment A and catchment B, the characteristics of the watershed are very similar. Okay, so let's say there is a general validity between these two catchments, that is catchment A and catchment B. So what we do, we calibrate the first catchment, that is catchment A, and then validate it with the other catchment, that is catchment B, and this is called the proxy catchment, right? And hence we call this as proxy catchment test. Proxy catchment test. Now the proxy catchment is treated as ungauged at the model estimation stage, but with some observation of the discharge and perhaps other variables which are available for the evaluation of the model prediction, right? And hence we call that as proxy proxy catchment test. Okay. So understood that what we do, we calibrate it for the catchment A, and we know that there is some hydrological similarity, or these two are hydrologically homogeneous, and hence we calibrate on one catchment and then validate on the other catchment. So these are some of the procedures that we have for validation. Okay. Okay. Then we have sensitivity analysis, right? So as I mentioned that during calibration, what we do, we estimate the parameters, isn't it? Now it might be possible, let's say we have, let's say, four parameters we have. Okay, four parameters can be, let's say, A, B, C, D. Okay, so it might be possible that each of these parameters represent something. Some process parameters are there, maybe porosity, no porosity are the physical parameter, maybe Manning's roughness coefficient or something like that, right? Now it might be possible that if A increases by 10%, then it responds to very high to the, let's say, the stream flow. Okay, so a little change in this parameter A can change the stream flow value a much. Okay, so this means what? It is very sensitive. It is highly sensitive. This A is highly sensitive. But whereas let's say B is increased to, let's say, 50% also, but still the response to the stream flow is neutral, is not changing much. Okay, this is neutral, I am saying. This is increasing, I am saying. Okay, and hence this parameter, that is parameter B, is not that sensitive, is very low sensitive. Okay, so that is kind of sensitivity analysis. So so before this, what we do, we also do the model evaluation. So in model evaluation, as I mentioned, we use several performance metrics or some graphical techniques, right? It can be time series plot or CDF plot, etc., right? So anyway, these are explained in the lecture. I'm not going very deep into this. So time series, I'm mentioning some of the previous slides also, right? So it can be, then it can be regression also, linear regression or something like that, right? We can use correlation coefficient or determination coefficient. Mostly this determination coefficient, that is R square, is very commonly used in hydrological applications. Okay. Then we also have dimensionless quantities such as index of agreement, then Nash, Sutcliffe efficiency, which generally mostly you'll see it as NSE, and Kling-Gupta efficiency, KG, and so on. There are several other dimensionless quantities also. After that, we also have error index such as mean square error or RMS, that is root mean square error, percentage bias, something like this. Okay, so these performance metrics we can use to evaluate the model, right? So that we can say, okay, with this model we are satisfied, something like that. Okay, so yeah, so while calibration, we deal with something called equifinality. What does this equifinality means? Equifinality means, like as I mentioned that, let's say again four parameters. Let's say A, B, C, D. Okay. Now it might be possible that a combination A, C, D is giving you a result or output one, and again B, C, D is also giving you some result, and both of these are satisfactory. It might be possible, right? Satisfactory. It might be possible that multiple parameter sets. So these two are parameter sets. Okay, so when multiple parameter sets provides equally good or acceptable model outputs, then we call that problem as equivalent, because we can't decide that which parameter we should keep, whether we should keep this set, that is ACD, or we should keep this set, that is BCD, right? So that problem we call as equivalent, and still this equivalent is, like, we have several procedures for it, but still this is one research topic. Okay, so one of the main sources of uncertainty in hydrological modeling is equivalent. Okay, so sensitivity analysis also is here. So mostly this sensitivity analysis, we have two methods. First one is the local sensitivity analysis, and second is the global sensitivity analysis. From the word local, you can understand that local sensitivity will help you in identifying which parameter have the most significant impact on the model results and how sensitive that model is to variation in those parameter. And hence in this what we do, we take one parameter at a time. We see whether that parameter is sensitive, highly sensitive, sensitive to the output or not, whether it is not that much sensitive, and so on, right? And so for this, what we used some sensitivity coefficients. So there are sensitivity coefficients such as absolute sensitivity coefficients or relative sensitivity coefficient. So in relative sensitivity coefficient, what we do, it is mostly unitless, because what we are doing, we are taking the change in the output to the change in the input into the input by output, and hence we get that as what do you say, a unitless quantity and so on. Okay. Yeah, okay. So with that, we'll do some questions, and then again we'll come back here. So we were here, right? Yeah. So now the question is, in hydrological modeling, parameters with high sensitivity, with high sensitivity. This means what? That parameter will be having much more impact on the output, and hence the correct answer will be, um, yeah. So the correct answer will be significantly impact the model predictions, right? Okay. Next question is, modeling protocol involves. So modeling protocol, as I mentioned, it is the modeling steps. So in modeling steps, we know that code development is one of the steps. Yes, model construction is also one of the steps. Performance criteria analysis is also one of the steps. That is model evaluation. So all this comes under some of the model protocols. There are other protocols also, calibration, validation, so on. So the correct answer for here will be all of the above, right? Yeah. So one questions we have seen that we'll do later was this one, right? So the question is, sorry. So the question is, the process, sorry, proxy catchment test involves. Just now we have seen that what we do, we calibrate the model against data for one catchment, and then we run that parameter on other catchment. And hence the correct answer will be A. Okay. Any question here? Okay, if not, we'll move to the next questions. Yeah. So we were here. So the next question is, three of the most important things to to consider when constructing a model are, okay, calibration, testing, model range, cost, time availability and skills, resolution, parameterization and testing, purpose, resolution and resources. Can anyone tell me what will be that? So the correct answer will be this D, that is purpose, resolution and resources. So this question is, while constructing a model. So while doing the model construction, hence calibration, validation still is the next steps or the next modeling protocols involved. Hence, while constructing a model, we need to have the perceptual model, that is purpose. Then we need to know what is the resolution and what all resources, that is field data, that we have. Okay, so the correct answer for this question will be D. Okay, so the next question is, physically based hydrological model. I think it didn't come. Yeah. A physically based hydrological model usually consists of one or more equations, right? Yes. It also have an initial state, boundary values, that is what is happening at the edge of our domain, and some input of change over time. So these are there, like equations. Sorry. Initial state, boundary conditions, and some input of change over time. Okay. So now you have to classify each of the statement as true, maybe true or false. Okay, so let's go through each of the statements exclusively. First one is the watershed ridge. Watershed ridge means the watershed boundary is a boundary, obviously, and there is usually no inflow from this unless water is being imported by a channel. Yeah, so this is true, right? Yeah. So next question is, the domain is always a rectangle of the land surface. This is not correct, because a watershed can have any of the um, domain, right? It can be any structure, any shape, any size. Next question is, for a physically based model, the parameters can, in principle at least, be measured by an appropriate laboratory or field setup. As I mentioned, the physically based model for some parameters like hydraulic conductivity or porosity. These are the parameters that we have. At least if you just say in principle, in theoretically, you can say that these physical parameters can be measured appropriately in the laboratory, or like if you do experiment properly. So this is also true. Next is the initial values are usually obtained by field measurements. Yeah, so sometimes these are what we get by field measurement, but sometimes we have the data problem previously, and then we can get the initial values, or by understanding also. So this is maybe true. The spatial arrangement of components is not usually a factor in the model. Yeah. So again, let's say depends on which kind of model you are using, right? So if it is a distributed model, obviously it will be a it will affect a much. But if you just consider as a lumped model, in that case, the spatial arrangement of the components will not be a big factor, right? So this again will be a maybe true. So yeah, so A and C are true, B is false, and D and E are maybe true. Okay, any questions here? Okay. If not, we'll move to the next question. The next question is the model based on fundamental physics and process governing equation is called as this we know anyway. We have seen this is process based model C. Okay. Next question is expand the term in a C, that is Nash-Sutcliffe efficiency. So the correct answer will be B, right? Sorry. Complexity of the model escalates from, so let's say if we go from smaller to longer time scale, this means we are easing our model, and hence the complexity will reduce from smaller to longer. So this one is not the correct answer for this. Next is process based to empirical relationships. So we know that process based relationship will have more complexity, right? So this is not correct answer for this. Next is larger to smaller spatial scale. Yeah. So if we go from the larger spatial scale to smaller spatial scales, so let's say from lumped to distributed, obviously the complexity of the model will escalate. So the correct answer will be C. Okay. Next question is Mike She is a lumped conceptual model, distributed physics based model. So this model, if you have seen, this is a used model. It is a used model, but Mike She's. So this is distributed physics based model. There are plenty number of models, as I said in the beginning also. So the correct answer will be distributed physics based model and light gray model. Okay. So the correct answer will be B and C, because we know some of the process that is involved in this, and hence we can call that as light gray model also. Okay, so the next question is example of joint stochastic deterministic model is, so stochastic joint stochastic deterministic model, we know Sacramento is one, then and NAM is one. So these are the joint stochastic deterministic model. Okay, so the correct answer is B. Next question is which of the following can be a model parameter? So model parameter can be catchment area, physical parameter. This can be the process. This can also be. So the correct answer will be all of them. Right? Okay. So the next question is model test procedures are, yeah. So all these three are okay. So all these three are non-control test is a trend test. Yeah, so the correct answer will be A, B, and C. Okay. Next question is when multiple parameter sets provides equally good or acceptable model outputs, we have seen this is equifinality, right? Correct answer would be equifinality. Okay. Next question is relative sensitivity coefficient can be expressed as this one B, that is dO by dP into d by O. Okay. Yeah. The sensitivity analysis of one parameter at a time occurs in local sensitive terms. We have seen this, right? The key difference between machine learning and deep learning methods are, so we know that these machine learning approaches and deep learning approaches comes from AI, that is artificial intelligence. So let's say if AI is a bigger circle, then machine learning is a subset of this. I'll write this as machine learning, this as TL, that is deep learning, and deep learning is again a subset of the machine learning. Okay, so what is the key difference between machine learning and deep learning? So the main difference is the feature extraction process, how you extract the process in the machine learning and the deep learning. So we have gone through all the in the lectures. It is very nicely explained. I'm not going very detailed into those. Okay, so the correct answer will be B. Next question is, which one of the following is not the classification of machine learning? Okay, so so these are the classifications: supervised, reinforced machine learning, unsupervised machine learning, and so on. So in supervised machine learning, what we do, we have data and we have labels also, right? So what we do, so let's say you have given several data to it. So let's say you have given several fruits, maybe like this apple is there, then banana is there. I don't go to my, oh, this looks like more chili than banana. Okay, let me just explain. Yeah, okay. So in supervised machine learning, what we have the data and we have the labels. So let's say you are saying that if some fruit, if it is like sphere kind of with in the top and bottom, it is little depressed. Okay, and it is like one fruit, and then from color you say. So based on some of the characteristics of that fruit, you are labeling it as apple. Okay, based on some of the characteristic of banana, you are saying, okay, this is banana, and something like that. Now this is while you are doing the kind of calibration, if you just analogously think, right? Now you are giving one fruit that while doing the model setup you don't know, and hence you are asking the model that whether what kind of app or what kind of fruit is this. Okay, that is the validation stage or testing stage, right? So in supervised machine learning classification, we have both the data and labels, whereas in unsupervised, what happened in unsupervised, so in unsupervised machine learning, it does not require predefined ground truth. Predefined ground truth, right? So what we are doing, it works with raw unlabeled data, allowing algorithms to discover hidden parameters. So you have given several fruits to the model and let them decide like what pattern is there in this, and then you can test it later. For example, let's say you have given several animals. Now you if you are saying, okay, this animal, let's say for example, dog, cat, then something like that. You have given several animals, and then the model will on its own will understand that what kind of pattern is there in all these data that you have given, and based on that, let's say after some time you are giving some animal and you are asking which animal it is. So that is also kind of testing stage, but here you are doing without the label, so you are not mentioning whether this is dog, this is cat, this is something like that. Okay, something like that. So based on the pattern only, based on hidden pattern, we get the information. And next we have reinforcement machine learning. So in reinforcement machine learning, what we have the sequential input and some action. So let's say uh, um, some agent need to understand, like they will observe and they will learn. So let's say they need to understand whether we need to go to the right hand side or left hand side, which one is the right hand side, which one is left hand side. Okay, now let's say if you have given one penalty, like if you go to right hand side, I um, you'll have to give me 500 rupees, right? If you go to left hand side, you don't have to give me 500 rupees, something like that penalty you have given. So that is the action that you have to take. So let's say if the agent is going to the right hand side, you have to give a penalty. So that is one action taken, and hence he will understand, okay, so now this is the right hand side, I don't have to go, something like that, right? So he will understand, or he or she, whatever model we have, the model will understand that, okay, so this is the right hand side and this is the left hand side, something like that. So that is called as reinforced machine learning. So here we are asking that which is not the classification of machine learning. So the correct answer is simple machine learning is none of the classification. Okay, yeah. So the next question is, dash algorithm is to create the best line or decision boundary that can segregate n-dimensional space into classes. So we have studied about several machine learning techniques like regression methods, neural networks, decision trees, support vector machines, nearest neighbor, and so on. Not going into the methods and all, but the algorithm or the method that gives you the best line or the decision boundary that can segregate n-dimensional space into classes is support vector machine, right? We guys have studied in the lectures. Yeah. So the next question is the most popular choices for model evaluation. I said that to understand whether this model is suitable for our purpose or not, we do model evaluation, right? In which we do the visualization or some statistical measures or some dimensionless numbers, something like that, right? So the most popular choices are uh, option A is cumulative frequency distribution, CDF, or R square NAC and RMSE percentage bias, or time series plot R square NAC and RMSE percentage bias, time series plot R square. Yeah, so the most popular is this one, the second one, that is time series plot. Because the time series plot you might have seen in the lecture also, it is a very important plot that you can see. Anything which you want to understand for some time series data, just plot it, and then from there you can get the first hand experience, first hand information or inferences from that plot itself, right? So time series plot is one of the most commonly or most important uh, first hand model evaluation you can do. Okay, then R square, NSC, RMSC, percentage bias, all this is the very commonly used. So the correct answer will be B. Okay, so the next question is which data is commonly used as input in hydrological modeling? Okay, so just for hydrological modeling, I'm saying, let's say for some rainfall runoff modeling. Okay, so for that, in this options, if you just see, it can be rainfall, temperature, or stream flow modeling. That can be the inputs or outputs. Okay, so all these options that you can see can be applicable for some of the modeling, not hydrological modeling, but maybe water quality modeling, some groundwater watershed modeling if you're doing something like that. Okay, so yeah, so the correct answer for this question would be rainfall, temperature, stream flow, right? Yeah. So the next question is we are done with the question today. Yeah. Any questions till now? If not, we'll stop here itself. No questions? Okay. So we'll stop it here. So we'll again meet next Monday.